We are standing on the edge of a massive revolution in computing. For decades, the goal was pretty simple. Just build faster machines. But now, that whole goal has changed. We're trying to build machines that actually think more like we do. This is the story of iontronics, a breakthrough that could finally, really, lead us to a true artificial brain. To really get why we need this revolution, all you have to do is look at the numbers. The human brain, probably the most complex thing in the known universe, runs on just 20 watts of power. That's less than a dim light bulb. Meanwhile, a supercomputer trying to do similar complex stuff, it can chew through megawatts of electricity, enough to power a whole small town. This absolutely staggering energy gap, that is the central problem that's driving the future of AI.
So the big question is, why are our incredibly advanced computers so inefficient? Well, the answer actually lies in a design decision that was made over 75 years ago.
It's something called the von Neumann bottleneck. You see, in pretty much every single computer you have ever used, the part that does the thinking, the processor, is physically separate from the part that does the remembering, the memory. And this setup creates a constant, totally unavoidable data traffic jam.
Just picture this. It's like a little shuttle bus. The processor needs a piece of information, so it sends out a request. The data gets loaded onto this bus and shipped over from the memory. The processor does its little calculation and then ships the result right back where it came from. Now imagine that shuttle bus running billions of times every single second. That constant back and forth wastes a tremendous amount of time and, you guessed it, energy.
And that, right there, brings us to this huge paradigm shift. If we can't solve this power problem by just making the shuttle bus go faster, then maybe we need to get rid of the bus entirely. We need to stop building computers like they're computers and start building them more like brains.
This is the absolute core idea behind what we call neuromorphic computing. It's a complete rethink of how a computer should be built. Instead of a separate processor and memory, it uses a network where information is processed and stored in the very same place, just like in a real brain. And here's the really crucial part. These systems are event-driven.
This analogy just explains event-driven perfectly. A traditional computer is like that guard just shouting, "Tree, tree, tree," all day long. It's constantly processing, constantly burning energy, even when nothing new is happening. But a neuromorphic system? It's like the smart guard. It stays quiet, using almost no power at all until something important, an event or a spike of new information, actually happens. It only works when it needs to.
But here's the thing. Just mimicking the brain's architecture is only half the battle. The real, honest-to-goodness breakthrough comes from mimicking its physical processes. It's a move away from traditional electronics and towards something that's a lot more like biological wetware.
Early attempts to build artificial neurons used standard computer chip transistors, but they were incredibly clunky and inefficient. Then along came memristors, which were definitely a step in the right direction. But the true game changer is the iontronic memristor. See, instead of moving electrons around like all other computers do, these devices work by moving ions, which are just charged atoms, exactly like the sodium and potassium ions that power our own brains.
So this switch to ionotronics doesn't just make the process more brain-like, it makes the hardware itself radically simpler and way more powerful.
Remember those old CMOS neurons? To get just one artificial neuron to behave even a little bit like a real one, you needed this complex circuit with tens, sometimes hundreds of transistors. It was bulky, it was complicated, and it was a real power hog.
And here is the absolutely amazing part. The new iontronic neuron achieves a far more realistic simulation with just 3 simple components. All that crazy complexity is just gone. This isn't just a small improvement, folks. It's a profound leap in simplicity and efficiency.
So how does it even work? Well, the magic is that the physical movement of ions inside this tiny device just naturally copies what a real neuron does. For instance, a biological neuron slowly builds up a charge before it fires, right? Well, in this device, that's just the natural process of tiny ion filaments growing and then dissolving. It even uses the natural randomness of that ion flow to mimic the brain's own creative noise, basically turning what used to be a bug into a feature.
Okay, so we have this tiny, simple device that acts just like a neuron. What does this actually unlock for us? Well, it opens the door to a future for AI that, until now, was pretty much pure science fiction. Let's start with the energy numbers, because they're wild. This new device can operate with an energy consumption as low as 415 picojoules per spike. Now, a picojoule is 1/trillionth of a joule. It is an almost unimaginably small amount of energy to perform such a complex task.
And when you look at this chart, you can really see the difference. The energy needed by those older CMOS neurons is orders of magnitude higher. This isn't just some incremental improvement, it's a fundamental leap in efficiency that's starting to close the gap between our tech and actual biology.
This incredible efficiency, it changes everything. It means we can finally have powerful AI running on tiny battery-powered devices. I mean, imagine real-time gesture recognition on your watch without it draining the battery in an hour. It allows for advanced biointerfaces. In fact, researchers have already used these to connect directly to a cockroach's nerves and control its muscles. We could even build drones that make human-like decisions, all on their own with very little power.
But as revolutionary as this all is, we really have to be realistic here. We have not yet built an artificial brain. The gap between our best technology and the real thing is still immense.
In fact, analysis shows that even our most advanced neuromorphic hardware today is still about 4 orders of magnitude, that's 10,000 times, less energy efficient than the human brain. We've made a giant leap, for sure, but the final mountain we have to climb is enormous.
And that leaves us with the ultimate question. We've gone from manipulating electrons to actually moving ions, and that's gotten us closer than ever before. But to close that final 10,000-fold gap, what's next? What new materials, what new understanding of physics will we need to finally truly build a machine that thinks?